just briefly before I move on to the Doppler effect. So let me compare and contrast with standing waves. Standing waves. What the idea is you have two waves that are in what's called a superposition. So superposition is basically that they're combining. And the two waves superposition is this. They have the same amplitude. They have the same wavelength. The only difference is that they're traveling in opposite directions. That's the big thing that forms a standing wave. The fact that the two waves are passing through each other. That's what causes it to look like it stands in place and you have these nodes and antinodes and stuff. That's what it comes from. Beats is just a second superposition that's slightly different. It's also a two-wave superposition. Two waves, also the same amplitude, but they are traveling the same direction. So what's different about them is that they, of course, if there was nothing different about them, then we would just combine them into one big wave, and it just would be no big deal. But they have slightly different wavelengths. So they have different wavelengths. So that is the big deal. Okay? So kind of see where the difference is in the action of these two superpositions. Standing waves, the big deal is that they travel opposite directions. In beats, it's that they're different wavelengths. So what happens when you have two waves that are like, one's like this, and one has a slightly different wavelength? What happens when you combine them? Well, it turns out what happens is that the two waves aren't perfectly the same wavelength, so if a crest and a crest line up at one spot, they're going to slowly go out of sync, right? And there will be a point where they kill each other, and then they'll come back again. So what happens is this. Let me try to... So make something like this. So if these are both have amplitude A, then you get this kind of strange wave that at the highest it has an amplitude of 2A, but there are also spots that it has an oscillation of none. So that's when the two waves slowly kind of go in and out of sync with each other. And I want to tell you the properties of this wave, and I'm not going to derive this. Let's say this one has a frequency F1 and a frequency F2. Of course, if they have different wavelengths, they'll have different frequencies as well, right? Yes? Is that okay? Because V equals F lambda. So if they're both traveling on the same stuff, the V will be the same. So if their wavelengths are different, their frequencies will be too. Here's the property of this wave. Its frequency will be the average of the two. But it will also, you can see that the amplitude varies, right? And we talked about the fact that amplitude is a measure of loudness, right? So we talked about the intensity being proportional to the amplitude squared. So what you will hear, this wave, you'll hear it as, right? Because the loudness will change. So we call the kind of, the warbling of it, we call that a beat, right? You kind of hear that. The beat frequency is actually the difference of the two. And you can put absolute values on it just so you don't accidentally turn negative, or you can just subtract them bigger minus smaller. This is often used to tune instruments. Let me show you. So if you play guitar, one of the ways you can tune a guitar, you don't want to compare notes by pressing down the frets, because then you can inadvertently change the tension just a little bit. So you want to use those harmonics that you have, right? Something like that. And what you can do is if you know that there's a harmonic on two adjacent strings that are supposed to sound the same, you can play them together and see what you get. So this one and this one on the next string. Right, so you hear that? They're supposed to sound the same, but if you have a good ear, you can tell they're not the same. So what you can do is you can play them together. You hear the wong, 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 wong. That's the beats. And the beat frequency, the loudness variation, will be how far apart the two are. So let me try to vary that. Now they're closer to each other. Let me make them further apart. So when I make them further apart, you hear it go faster. Wah, 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 wah. Oh, gotta get both of them. You hear it warbling faster. The more apart they are, the faster the beats will be. Wah, 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 wah. That indicates the frequencies are further apart. When it starts to go wah, 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 and you start to hear the beat frequency get small and small and then disappear, that means you have the two strings tuned properly, right? So you're trying to get, what you're actually hearing when you play them together is the average. So you can't actually even tell when you're playing them together that there's two notes. What you hear is their average, and the beat frequency is the difference in the two. So for instance, if you're hearing the beat frequency at 1 hertz, right, which is 1 cycle per second, wow, 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 that means they're 1 hertz apart. So what you're trying to do in your tuning instrument is you're obviously trying to get rid of the beat frequency. You're trying to make it so that the beat frequency is so, the difference between these two is so small that the frequency is so small that it's basically going away, right? Instead of wong, 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 which is a large frequency, to wong, 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 it's a smaller frequency, they're closer, to wong, wong, that means they're really close. So the smaller the beat frequency gets, the smaller the loudness variation, the closer you are to tuning it. Are there any questions on that? You can imagine that as the two frequencies become exactly the same, they're not going to phase in and out with each other anymore, right? So you're not going to get this amplitude variation anymore, right? The whole amplitude variation comes from the fact that the wavelengths are different and the frequencies are different. Okay, are there any questions on that before I move forward? Okay, so let's move on to the Doppler effect. So if you don't know the name of it, you've probably experienced this. If you've ever been standing on the street corner and heard like a police siren pass or a fire truck, anything that's making noise, maybe even just someone playing loud music out the car, you hear a frequency shift as they pass, right? So if maybe someone's just laying on the horn and they drive by you, you hear right? You hear this higher to lower frequency. It's not a loudness variation, although there is one of those too. Obviously, if someone's driving toward you, the sound gets louder. They drive away from you, it gets quieter. It's a frequency variation. It's a shift in the note, right? So let's talk about where that comes from. So here's you, standing, observing the situation. I'll call O for observer. Let's say you're standing still. And you have a car that's going to drive by. I'll call this the source of the sound. So S here is going to stand for source. Those are going to be my letters, O and S, observer and source. Now, that car, when it's laying on the horn, it's putting that sound in all directions, but obviously you don't hear all the sound. You hear the sound wave that just comes toward you. So let's talk about what happens. So let's say I am in the car, I'm letting out sound waves that are going forward toward the observer, and those sound waves have to travel at 343 meters per second in the air. You guys measured the speed of sound earlier. But here's the thing. if you put out a crest, so you put out a crest at 343 meters per second, but then you drive into your own wave a little bit, right? You're moving forward. So you throw off that crest at 343 meters per second, but you catch up to it a little bit, and you let the next one go a little closer than it would have otherwise, right? You're driving into your own wave. And so what that tends to do is you tend to smush your own wavelength, right? So the wavelength is smushed. Those crests are getting bunched up together because you're driving into your own wave. Remember, the crests have to travel 343 meters per second relative to the air, but you're also moving in the air. And so if you're, say, traveling at 10 meters per second, then you're going to let that crest you just released is not going to get as far away from you as it would if you weren't moving, right? So if you're moving into the wave, those crests get compressed. So if we look at v equals f lambda, this is fixed, right? 343 meters per second. So if you smush the wavelength, what's going to happen to the frequency? It gets up, goes up. So the observer is actually going to observe a higher frequency than was emitted at the source. If the wavelength is compressed, then the crests are closer together. The observer is going to hear them more often, right? That's frequency, right? It's how often you get those crests. You get them more often if they're compressed, okay? All right, let's do the other case. The car drives away, so it passes you. Now, of course, it sends sound out in all directions, but we're only concerned with the sound wave that reaches the observer. That will be the one that goes backward. The opposite direction is the car. So I guess I'll add another ear here. Oops. I don't know what happened with that ear. So let's think about that, right? You're driving, you let it crest out behind you at 343 meters per second, but then you drive away from your own wave, right? So you let that crest out into the air, and then you drive a little bit away from that before you release the next one. It's going to elongate, stretch the wavelength, right? So to greatly exaggerate, it's going to look like this. The wavelength is stretched. And if the wavelength goes up, what happens to the frequency? It goes down. So the observer will hear a smaller frequency than was actually emitted by the source. You hear a higher frequency when the car is coming toward you. You hear a lower frequency when it goes away. Higher pitch to lower pitch. Right? It's always that way. It never goes that way. It goes always higher to lower, right? That's because when something's coming toward you, the frequency is lifted, and when it's driving away from you, the frequency is lowered. Okay? All right? So that's the general idea of the Doppler effect. It's that the relative movement of the observer and source can cause this frequency shift, because the wave that travels between them is forced to travel 343 meters per second relative to the air. And so if the source of the sound is moving, it can either stretch or compress the wavelength. Okay? Now, the other thing I should mention is that it's really only relative motion that's necessary. You could do it the other way. You could have that the car is parked, so this is a source, but you run really, really fast toward it. Whoa, I don't know what happened with that foot. There we go. So you could run really fast towards this, right? As you observe it. That's another way to experience the Doppler effect. I'll give you an example, right? Let's say you're out at the beach. Your friend is standing in the water saying, hey, water's fine, come on in. Waves are going past, crest, crest, crest. So you say, okay, I'm coming in there, and you run at top speed to go in the water with them, you get press, 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 pressed, right? You experience getting hit by waves faster than they do. Not because the waves are doing anything different, but your friend is just standing there letting the waves pass. You're running into them. So of course you're going to get more crests. Does that make sense? So that's another way that you could have, that you observe a higher frequency of waves than is actually being emitted, is by you running into them. So notice it doesn't matter if the source is moving toward the observer or the observer is moving towards the source. The important thing is that if the distance is closing, right, so these two cases, it doesn't matter if the car is going towards the observer or the observer is going toward the car, the source. The important thing is that there is a relative closing of the distance, right? And so for that, let me introduce my rule of thumb. If the distance between the observer and source is decreasing, it's getting smaller, then the observed frequency is higher. We call it an upshift. If for any reason, so it doesn't matter if it's the source moving toward the observer, vice versa, maybe they're both moving toward each other. As long as the distance is getting smaller, then the observer will experience an upshift, a higher frequency than was actually emitted. Likewise, if the distance between them is increasing for any reason, I drew here, of course, that the reason why the distance between them is increasing is because the source is moving away while the observer is stationary. But it could be the opposite, right? So I could have that the observer runs away from the source. As long as the distance, for whatever reason, is increasing, the observed frequency will be less than what's actually emitted. We call that a downshift. So this is my rule of thumb that you can always count on, so that when you work out the results of the equation I'm about to give you, you can always do a basic head check to make sure that the results agree. Anytime the distance between them is changing for any reason, there will be a Doppler shift, and which way the shift is dependent on if they're getting closer together or further apart. Okay? So, without further ado, I would like to jump straight to the master Doppler effect equation. The equation will give you what is the frequency that is observed, and the raw ingredient, one of which is, of course, the frequency of the source itself, but there's, of course, going to be something in that parentheses so that the answer may not be always the same, right? So the frequency observed is generally not going to be the frequency that the source itself emits. So here is my equation. It looks like this. It may look intimidating, but I'm going to show you how to use it. So, the first thing I want to point out to you that V in this equation, just like in all of our equations, is a speed. It's plus, right? When we say V without a vector hat, it's not velocity anymore. It's the size of the velocity, which we call speed, right? So positive numbers are going in for all of the V's. There's 3 different V's, VO, VS, and just V. What are these? Well, we already said that O and S are stand for observer and source. So VO is the speed of the observer, VS is the speed of the source, because we said generally both can be moving, right? So we want to, in our master equation, we want to account for the fact that they might both be moving with respect to the air, okay? It doesn't have to just be that the source is moving and the observer is stationary, or the observer is moving while the source is stationary. They could both be moving in some way. What's the V just by itself? So VO is the observer speed, Vs is the source's speed, and the V without anything is this 343 meters per second. It's the speed of sound in the air. So, notice that the speed of the observer and source is always taken as a ratio to the speed of sound in air. That has an important implication. Okay? So, if VO over V and Vs over V, those might be relatively small fractions. Okay? So, the speed of sound is 343 meters per second. That's very fast. Normally, an observer or a source is not moving nearly that quickly. So if these ratios are small, then adding or subtracting from 1 is not going to make too big of a difference, right? So if that's small, the observer and source frequencies are about the same. So as I'm pacing back and forth here, you don't hear violent pitch shifts in my voice, right? And even when a car drives by laying on the horn at, say, 40, 50, 60 miles an hour, your Doppler shift is maybe a few hertz. Not, right? You never hear that. Something would move, if something moved by you fast enough, you'd hear that. But even a car cannot drive at a huge a fraction of the speed of sound. Okay? So this effect is small, and it's small because the speeds of the observer and source are not usually relatively small fractions of the speed of sound itself. Okay? Does that make sense? Then I guess I should mention there's another form of this formula that you may like better. If you're ever forced to compute without a calculator, you might prefer this. What you can do is you can multiply both the numerator and denominator by the speed of sound. Then the equation looks like this. Let me put it over here. So an alternate form of this equation that if you have a calculator, it doesn't really matter. I like this form because it lets you remember that these ratios are small and then the ratio is about 1. But you can also express it like this. It looks like this. So that's just basically what we call in math rationalizing it by multiplying the top and bottom by the same number. And so there, I guess it's not really that much harder to see, right? If VO and VS are very small fractions of the speed of sound, then you basically get V over V here, and that cancels, right? Question?
Is there a reason for the denominator where you put the minus over the plus?
Oh yeah, so I'll talk about the signs in just a moment. So in fact, let's do that right now. The signs are designed for just using the equation without worrying, like basically everything's all arranged for your ease. Here is the, here's how you choose the signs. The top signs, the numerator signs, are for what the observer is doing. Now, hopefully that's obvious because it's right next to the observer. The bottom signs, the denominator signs, are for what the source is doing. They can both be moving. So which one do you pick? Well, it's made so the top sign in each set is the towards sign. So top, remember, top is towards. The top sign in each set. So for instance, if the observer is pointed toward the other guy, then you pick the plus. Now it turns out in the denominator, if the source is pointed toward the other guy, you should pick a minus, so that's why the minus is on top, so then it's just for your ease. Remember, top is towards. And the bottom sign in each set is the away sign. I don't have a mnemonic for you there, but of course, if top is towards, there's only one thing left. Right? So T is top, T is towards. So let me show you a couple quick examples of that, how to choose these signs. So let's say I have the observer and the source like this, let's say. And let's say they're moving towards each other like that. So each of them is pointed toward the other, right? So then we pick the top sign in each set. So in my equation, I would choose on the top, I pick plus, and on the bottom numerator, I pick minus, right? I pick the top signs in each set, right? And I want to point out that since they're going towards each other, we're going to get a big upshift, right? The distance between them is definitely decreasing, so we're going to get an upshift. So we have a bigger numerator, right, because we're adding, and we have a smaller denominator, both of which are going to make the number go higher, right? If we want to make the fraction higher, we make the numerator as big as possible and the denominator as small as possible. So we're definitely going to get an upshift here. And the rule of thumb is what we used as a head check. And luckily, the equations seem to agree, right? Bigger numerator, smaller denominator, that's going to result in a bigger number. Let's do another one, though. Let's say that the observer is going toward the source, but the source is going away, something like that. So let's pick the signs, practice. So the numerator, that's for the observer. Is the observer pointed towards or away from the other guy? Towards. The observer is pointed toward the other guy. Okay, so which sign do we pick, plus or minus? Plus. All right, the source, denominator. Is the source pointed towards or away from the other guy? Away. So which sign do we pick? Plus, the bottom. Here, whether we're going to get an upshift or a downshift is inconclusive, right? We're making the numerator bigger because it's going to be an addition, but the denominator is also getting bigger. So this could be an upshift, a downshift, or no shift. In fact, what if these guys were moving at the same speed? What if VO was the same as VS? What fraction would we get here? 1. Right? Because it's 1 plus the same thing, 1 plus the same thing, they would cancel. Does that fit with our rule of thumb, though? Is that okay? Yeah, because if they're moving at the same speed, there's no distance change between them. So there is no Doppler shift. You have to have that the distance has to be increasing or decreasing. There will be no Doppler shift here if they're moving the same speed. If their speeds are different, then the distance will close or open, right? Then we will see a Doppler shift. Let's do one more. Let's say that there's a source, there's the observer. Observer is moving like this, and the source is stopped. Let's try that one out. Okay? So numerator, observer. Which sign do we pick? Away, right? Observer is pointed away from the other guy. Here's a common source of confusion. Which way is the source pointed? Towards or away from the other guy? Isn't. Which sign do we pick? Doesn't matter. It's 0. 1 plus or minus 0 is the same thing. So this, it doesn't matter. If you're going to put in 0 for the speed, then you don't have to pick a plus or minus anyway. Okay? So that's how you select signs. And hopefully you see that even though there's this big master equation that we didn't necessarily go through the trouble of deriving, it's kind of set up for you to just plug and chug it. Okay? So what do? You put in what is the original source frequency, and then this fraction is designed to tell you by what factor does the observer hear something different. You put in the observer speed, if any, source speed, if any, take them both as fractions of the speed of sound. The signs are set up, they might look funny, it's plus minus and minus plus, but they're set up so the top sign in each set's the towards sign and the bottom sign in each set is the away sign. And you just pick it and go for it. So with that in mind, let's do an example problem. So we'll do a problem from scratch and see if we can get through it. So here's my problem. Okay, I'm going to read it here. While on vacation in Costa Rica, you look over your shoulder and see a velociraptor. Okay. You begin running away at a speed of 9 meters per second. All right, so let's draw this. Can't draw a velociraptor. I don't know what that looks like, a big fish, but sorry. Okay. So you begin running away at a speed of 9 meters per second. I guess I should label this as an example. Just a physics example. There are no velociraptors in Costa Rica, as far as I'm aware. So you begin running away at a speed of 9 meters per second. As you look back over your shoulder, you hear the velociraptor's war cry at a frequency of 1260 hertz. Okay, so you observe 1260 hertz war cry. Okay. And notice that it is 100 meters away. We know that a velociraptor war cry actually has a frequency of 1200 hertz. So the actual frequency of the source is 1200 hertz. And the question is, how long before you are eaten by the bloodthirsty dino death machine? Okay? T sub Eqns, okay, is what we are looking for. All right? So, first of all, will you be eaten? Yes, because you are observing a higher frequency than is actually being emitted. And if you are observing a higher frequency than being emitted, the distance is decreasing. Okay? So, let's figure it out. So we go into our equation. I guess I'll just recopy it here. So your observed frequency is 1260. Your actual frequency is 1200. Let's pick some signs. Okay, so the observer, numerator. Are you pointed towards or away from the velociraptor?
Away.
Away. Okay, so which sign do we pick?
Minus.
Minus, the bottom. Okay, and you're going at 9 meters per second, which is not a very large fraction of the speed of sound. Okay, let's do the denominator. Well, the denominator is the source, the velociraptor. Is it pointed towards or away from you? Towards. It has to be towards, because if it was stopped, you would be increasing distance from it, and you should hear a lower sound. So it's obviously coming to eat you, okay? So this is velociraptor. The source of the sound is this way. And we're actually going to figure out what that is. That's going to help us to figure out how long it takes to eat you. Which sign do we pick there? The minus, right? It's toward you. So toward, the top is towards. That's a minus here. So Vs over 343 meters per second. So that can be solved, right? So you're going to solve for how fast the velociraptor is moving. To not bore you with the algebra, you can work it out at home. The speed of the source here is going to be 24.9 meters per second. All right. So while you are trying to run away at 9 meters per second, it's way faster than you, and so the distance is closing, right? The distance is decreasing. That's why you're hearing a higher frequency than it's actually emitting. You hear 1260, it only emits 1200 in actuality. All right? So that's not what the question asked exactly. It asked how long till you're eaten, right? So we have to figure out if this is 24.9 meters per second. Now you can certainly delay your death, okay? What would be the relative speed at which they're moving to each other? How would we do? We add those two or subtract them? We subtract them, right? So the relative speed, it would be nice if you could run away as fast as it ran toward you, then of course the distance would be closing. But the relative speed would be 24.9 meters per second minus 9 meters per second, and that would be, what is that, 15.9? So you're going to be able to delay your death. So effectively, that would be like if you were standing still, but the velociraptor was moving slower, right? So let's just figure it out then. Just use good old distance equals rate times time, right? The distance is 100 meters, but the rate at which it's closing is 15.9 meters per second. We can solve for t, okay? So the time until it gets to you will be 6.3 seconds. That is how long you have to live, okay? Are there any questions on this example? Okay, so you have several questions on your homework that are in this vein, using the same master equation, taking your signs, and so forth, right? Is that all good? All right, so let me go and show you another application of the Doppler effect. This is a property of all waves, sound waves. You can also do this with light waves, okay, too. So let me tell you a little bit about light waves. Visible light, you may know the colors of the rainbow, the acronym ROY-G-BIV. You guys ever heard of ROY-G-BIV? Okay. Red, orange, yellow, green, blue, violet. Okay. Those are the frequencies of visible light with increasing frequency going this way. So red is the lowest frequency and violet's the highest. There are, of course, light that is lower and higher than these. Just lower frequency than red is called infrared, and just above violet is called ultraviolet. Right? So, can we do a Doppler shift with light? Yes, we can. So, if the distance between the observer and source is decreasing, then we will have an upshift. Right? So, if we have that the distance between is decreasing, you will move to a higher frequency. This is called, for reasons that I'm not entirely behind, it's called a blue shift. I think it should be called a violet shift. First of all, why blue? But it's also, it doesn't mean you necessarily turn blue. It just means you go toward it, right? So you go toward it. So for instance, if I had a yellow shirt on and I ran toward you fast enough, I could, so the distance has to decrease, right? If I ran toward you fast enough, I can make it turn green for you. If I ran even faster toward you, I can make it turn blue or even violet. Okay? So again, this is called a blue shift generically. But again, it doesn't mean it turns blue, it just means it's increased frequency. It's toward the blue. Now, you've probably never seen someone running towards you and their shirt turned color. And the reason why is if the Doppler effect is hard to do with sound because the fraction of the observer and the source is always indexed against the speed of sound, which is 343 meters per second. That's hard to do, is to travel that fast, right? Well, it's even harder with light, right? It's going to turn out that the speed of light is 3 times 10 to the 8th meters per second, so good luck trying to go appreciable fraction of that, right? Now, I should mention briefly here for full disclosure, the actual formula for the Doppler shift for light is a little different. And that's because of all this fancy stuff called relativity. but the ideas are the same. The idea is that you'll see more of a shift the more you can go the fraction of the speed that the wave itself travels. So you don't really see the Doppler shift with light in any kind of normal circumstance. I guess I should mention that it's also possible to go the other way. Of course, this is when the distance between the two things is increasing. Then you will shift to a lower frequency. And this is called, probably more properly, a redshift. It's toward the red. It doesn't mean it turns red. It just means it goes more toward red. So if I were wearing a green shirt and I ran away from you fast enough, you could see it turn yellow. And even faster than that, you could see it turn orange or even red. Okay? So these red shifts and blue shifts might indicate something about relative motion. Now, there's nothing on Earth that really tends to travel fast enough, but if you look through a telescope, there are plenty of things in the universe that are moving fast enough relative to us that you can see them, the light that's coming from the Doppler shift. So for instance, if you look through a telescope and you look at a star out there that's just like our sun, and we have every understanding that what's going on in that star is exactly what's going on with our sun. You can look through it and look at something called the spectrum of it. Maybe you guys have talked about that in chemistry. We'll talk about it in physics too as well. This idea that you can see light coming from it that's characteristic of whatever atoms are contained. Only you notice something interesting. The light is shifted. So it's just like our sun, except everything is shifted a little bit to lower frequency. What does that tell you? Is that completely different physics going on in that star than our own sun? It just means it's what? It's shifted to a more lower frequency. It means how is it moving relative to us? It's moving away from us. Okay? So you can do a survey of the sky, and you can find out that most things that you look at, based off the Doppler shift of their light, are moving away from us. And the further they are from us, the faster they're moving away from us. So what gives? Are we the most unpopular place in the universe? Well, no. It's the fact that if everything is riding a piece of an explosion, then everything is moving away from everything, right? And if everything is moving away from everything, we're riding a piece of an explosion, then if you look at a very distant piece, of course that's going to look like it's moving that much faster away from us because, of course, if everything's moving away from everything, then everything in between has to also be moving away. And so what you see in an explosion is that the things that are nearby tend to be moving away from you somewhat, and the things that are further away from you appear to be moving even faster. And that's, of course, important because these also have to be moving apart from each other, right? So it would be odd if we saw that everything was moving away from us at the same rate. That means everything else is maintaining its spacing while getting away from us, right? One of the characteristics of an explosion is that if you look at any given piece, if you're observing from any given piece, the things that are near you are moving away more slowly, and the things that are moving away from you that are further away look to you like they're moving even faster. So this is primary evidence of what? The Big Bang. You can look and you can see that everything's flying apart, and you can extrapolate, okay, how far is it? How fast is it going? When was it all in the same place? So you can look. The Doppler effect is one of the things you can do to have evidence of the fact that the Big Bang happened. So most things that you look at are redshifted, and the further they are away from us, the more redshifted they are. Okay, so that'll do it for the Doppler effect. That'll do it for your homework 12. That will do it for new material in Physics 1. So on Monday, I'll talk about the final, and I'll do some review.